So welcome back, everyone. Today we are discussing about the Viterbi algorithm in the context of hidden Markov models, HMMs, and the question that sometimes students often ask, usually about a week after we discuss the HMMs and Viterbi algorithm, is that does the Viterbi algorithm not use Bayes theorem? Now, as you may recall, the Bayes theorem says that P of x given y is equal to probability of y given x times probability of x divided by probability of y. And why is Bayes' theorem itself such a central theorem in computer science and AI and machine learning? Because X usually stands for the root cause and Y usually stands for the symptom. So the equation is usually written as probability of root cause given symptom is equal to probability of symptom given root cause, which is we usually know, that's base knowledge, times the probability of root cause divided by the probability of symptom. So essentially, it allows us to switch the probability to find this probability of a root cause given a symptom, because usually that's what we're interested in. We're seeing the symptom and we want to understand what is the probability of this particular root cause, which could be a disease or whatever. And HMMs have very, very wide applications. And this is usually what a HMM overall looks like, that there's the true state, which is called the hidden layer. It can evolve. It has a certain transition function, transition probability, and it has a certain correlation with the emissions. So we observe those outputs. We also call them effects or evidence at each step. And using those observations, we want to make some inferences about the hidden layer. And again, there are many applications of HMMs. So this is the Viterbi algorithm. Again, if you want to understand the Viterbi and HMM, watch the full video that you should probably see linked somewhere. So that's the full video on the Viterbi algorithm. Here, I'll only touch upon it a little bit. The key step inside this is the dynamic programming, the left to right step. It builds a data structure, which is a two-dimensional array, which is this MP array. And it has, you can think of it as, it has number of as many states, that many rows, and as many observations you have, that many columns. So it essentially has n times k double matrix, and it builds this particular matrix from left to right. So each column essentially depends upon the previous column and doesn't really depend upon anything other than that. So this is how you write each step. You essentially write, if you look at just on these two lines, MPJI, this is essentially when you're filling one particular value in that matrix, and you look at the previous column, you find the maximum over the previous column that gives you essentially the maximum over of this particular value. This is the previous column value, MPZI minus 1, and you multiply that with the transition probability. Z corresponds to the row, so Z times J, and times the emission value, the emission probability, MJ, to give EI. We're currently talking about EI. Again, watch the full video if you have to. But if you look at this particular function, you don't really see any mention of Bayes theorem, etc. So the question is, does it not use Bayes theorem, or does it use Bayes theorem? So that's really what we're discussing here. So if you think about a single coin toss here, consider your single coin toss here. In this case, you have two coins. Let's suppose you have two coins, fair coin and a biased coin. And you have a fair coin, which gives heads and tails with a 50% probability each. Biased coin always gives heads. You toss a coin, you don't know which one was used, but you observe that the outcome is heads. So the question is, which coin was more likely to have been used? And this is a straight example of Bayes theorem. So let's calculate it. So what we want to compute is, we want to identify what's the probability of fair coin, given that we have seen heads. And we want to compare that with what's the probability of biased coin given heads, and then just take the maximum value. So what is the probability of fair coin given heads? So using the Bayes theorem, it's probability of heads given fair times probability of fair divided by probability of heads, and similarly for biased as well. So let's calculate it. What's the probability of fair given heads? That's equal to probability of heads given fair. That's half. What's the probability of fair coin? That's half, because these two coins could have been used in half with equal probability each. And for probability of H, we have to compute it. And we need it for both of these both of these expressions. So let's compute it separately. So probability of heads could have been either you were using fair coins and got heads, or you got biased coin and got heads. So that's equal to half times half plus half times 1. So essentially, if you were using fair coin, which the probability of that was half, then the probability of getting heads was 1/2. So that's 1/2 times 1/2, 1/4, plus probability of biased coin being used, which is half, and then the probability of heads given biased coin. So that's essentially equal to, that's 1. So therefore, total is 3/4. So therefore, when we go back to computing this thing, we can now plug in 3/4 on the two denominators. And therefore, we can now complete our calculation. So probability of fair coin given heads is equal to 1/3. Probability of biased coin given heads is equal to 2/3. So therefore, we can say that biased coin was the most likely explanation. And in this case, we did use the Bayes theorem. So it seems that we should basically be using the Bayes theorem altogether. Fair. But now, nothing to do with the fair coin, but fair point. Now, here we make one observation, that we did this calculation of calculating P of H. But now if you go back to finding P of H, you actually didn't really need to know this thing, because you were just trying to compare which one was larger. And the numerator was larger. In fact, it was twice. So you already knew that biased coin was the most likely explanation, even if you had never calculated this expression here on the right with the probability of H. That's 3/4, because it was a common denominator. Okay, so hold that thought. That's an observation to make here. And when we come to it, maybe we will see what we do with that. Okay, so going back to the Viterbi algorithm, in the case of a single coin toss, where it seems we use it, but in the Viterbi, we don't really see the same kind of math. So let's go back to the Viterbi algorithm. So to be precise, Viterbi algorithm does use the same exact reasoning. It just doesn't use the Bayes theorem per se, but it does use the same reasoning. Let's walk through the reasoning. So the most likely explanation asks us to find the argmax of x given E. So that means that given your observation that you have made, which x is the most likely explanation. So that means find the x which has the maximum probability of x given E. So that's what you want to find. And if you make a note that x and E are both, essentially they're both arrays, because we're not talking about one coin toss and one observation. You're given an observation, so you want to track what was the underlying state during those n observations. So that's why we can write it as x1 through n given E1 through n. So that's what we want to write here. Now, using Bayes theorem, we would say that this is exactly equal to x given E is equal to E given x times x divided by P of E. This is exactly what Bayes theorem would suggest to us. But now we can make an observation that, first of all, this does not depend upon the denominator. So therefore, we can actually drop the denominator. So this is what it wants us to find, but the denominator is not a factor for us. We might as well get rid of it and save that step, because we only need to find which x value maximizes it, and denominator is common. So we get rid of it. And therefore, we now have this particular expression left. And this is a key observation. This is also what we made in the case of a single coin toss. Going further, let's go further. What's the probability of E given x times probability of x? Let's just focus on this thing here, x given n. This is equal to x1, x2 given x1. This is the nature of the Markov model, that x1 through n, because this is a Markov model here, that means x2 really depends just upon x1. Well, there's only one x1 to begin with so far, so that's clear. x3 theoretically could depend upon x1 and x2, but because it's Markov, it just depends upon x2. So therefore, probability of x1 through n can be written as x1, x2 given x1, x3 given x2, and so on and so forth. So each of them is just one xi given xi minus 1. You don't really worry about what happened much prior. You just say what was in the previous state. And now similarly, if you focus on this one here, E1 through n given x1 through n, that's equal to E1 given x1, E2 given x2, again because of the Markov model. So given x1, given x2, e2 given x2, you should have more precisely written as e2 given x1, x2. But again, because it's Markov model, e2 given x1, x2 is equal to e2 given x2. So you don't really care about what happened in the past, just what is the current state, and that's what's going to drive your current and your future. That's again a key property of Markov. So now we can essentially, we just write these two terms here. And now we can rearrange these terms a little bit so we can, because we're building this in a recursive structure. So that's what I would focus on here. So now if you go back to the, let me get rid of this annotations. Let's go forward here. So now in the dynamic programming, this is what you would see is your yellow highlighted portion, MPZI minus 1. All of that is something that you have already computed. Then you just look at what's the transition probability. That's this highlighted area here. And this highlighted area here. This is your emission probability, which is what you see in the M here. And this is the stuff that's still to come. So this is basically the reason that it appears we're not using Bayes theorem, but we pretty much are. We just got rid of the denominator because denominator was common. Denominator was a common term here. So again, Viterbi algorithm very much uses Bayes theorem. I don't want the Bayes to be offended that we're not using the Bayes theorem. We very much are. You're very much using the same structure. The Viterbi algorithm is just an efficient algorithm, drops the term that does not affect it, and is able to do its calculation again. As you saw in the previous video, it does it in nk squared time, building an array of size n by k here. Okay, that's all I have on this topic. So have fun, keep learning. Okay.